So we've learned about different intermolecular forces, forces between molecules. We've talked about London dispersion forces, induced dipoles, dipole-dipole interactions, hydrogen bonds. But the reason those are important is because they allow us to predict and explain different properties of matter. So some of those properties that we've already talked about, we've talked about boiling points of substances. Why do some substances have different boiling points than others? We've talked about melting point. Why do some substances melt at different temperatures than others? We've talked about surface tension as well. And today we're going to talk about two more. We're going to talk about vapor pressure, and then we're going to talk about viscosity. So the first thing we need to know is, what is vapor pressure? Well, vapor is just another word for gas. So essentially vapor pressure is gas pressure. But it's not just the pressure of a gas by itself. It's the pressure exerted by a vapor or a gas that is in contact with a liquid. So it's not just the pressure of a gas in a room, it's the pressure that that gas is exerting on a liquid of the same substance in the liquid phase. So for example, let's say over here we have a beaker filled with H2O in its liquid form. Each purple sphere represents a water molecule. H2O, 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 H2O. And this beaker is in a larger container that has a sealed lid, sealed off. Okay? Well, we know that over time, like if you leave a cup of water out on a table overnight, the amount of water in the cup is going to decrease because the liquid water evaporated and turned into a gas and then floated throughout the room. So if we start with a beaker of water, we place it inside here, we know that some of these molecules are going to gain some kinetic energy from the heat in the room, and they're going to gain enough kinetic energy to evaporate and turn into vapor, to be more spread out and have more kinetic energy. And this is going to keep happening and happening and happening. Water, liquid molecules are going to turn into H2O gas molecules. So let's say we move to phase 2 now. Okay. Molecules are still evaporating. Okay, we can see the red arrows. They're still evaporating. But some of those molecules, since we're in this sealed off container, are going to bounce around, boom, 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 and eventually they might come back into contact with the liquid, H2O liquid. When that happens, some of those gas molecules are going to return from the gas phase back into the liquid phase because they're colliding with the liquid. Okay? The rate at which the substance is evaporating and condensing, the rates are different at this point. Right now, H2O is evaporating faster than H2O is condensing. That's why we can see the greater than sign here. Okay? But eventually, over time, these two rates are going to equilibrate, and the rate of vaporization of molecules turning from a liquid into a gas is going to become equivalent to the rate of condensation, where gas molecules turn into a liquid. And at this point, at this equilibrium, this is called equilibrium, when the rates are equal, okay? When these molecules that are in the liquid phase, the gaseous phase, vapor phase, collide with the liquid, they exert a pressure on the liquid. And if we measure that pressure at equilibrium, okay, we are measuring the vapor pressure. It's the pressure exerted by a vapor, by a gas, as it collides with the liquid. Well, how is this important in relation to intermolecular forces? Well, the idea is if a substance has high intermolecular forces, has some hydrogen bonding going on, and London dispersion forces is a very large molecule with a lot of surface area, very high polarizability, then there's going to be more attraction between molecules. If there's more attraction between molecules, that means the molecules are going to be held closer together. So there are going to be a decrease, fewer molecules that turn from a liquid into a gas. Because the molecules are held together, they're more attracted to each other because of the increase in intermolecular forces. So they're not going to turn into a gas. They're not going to evaporate that fast. So if there's fewer gas molecules, less vapor, that means we're going to have a decrease in collisions between the vapor and the liquid. And if we have fewer collisions, that means we have a lower vapor pressure. So the idea, in a direct one-step linear term, if we can condense all this, is if you increase the intermolecular forces of a substance, you are going to decrease the vapor pressure of that substance. So now we can solve problems where we are comparing vapor pressure of two substances and explaining why one substance would have a higher vapor pressure or a lower vapor pressure than another. It will be based on the amount of intermolecular forces. So you need to be able to walk away with this understanding, with this train of logic here that I'm circling in blue, as well as a definition of vapor pressure. The other concept that we need to discuss is viscosity. Viscosity. Okay? This is an O. Okay. Viscosity. What is the formal definition of viscosity? Well, viscosity is a fluid's resistance to flow. And this is best understood with examples. Okay? So for example, you had a beaker of water and you had a beaker of honey. Nice, delicious, sweet honey. Okay? And you decide to pour them out. Oops. Which will pour out faster? Well, from our daily experience, we know that water is going to pour out a lot faster, indicated by more blue flown out, than honey. Honey is going to come out a lot slower. So this is indicating that honey is more resistant to flow. It doesn't want to flow as much as water does. So honey has a higher viscosity than water does. Now we have to connect that to IMFs. Well, the idea is pretty simple. Substances will flow slower if they're attracted to, if molecules within that substance are attracted to each other more. So if you increase intermolecular forces in a substance, again, you're going to increase attraction between molecules. And if you increase attraction between molecules, you're going to increase viscosity. So 4 things to walk away with today: definition of viscosity and how IMFs affect viscosity, as well as a definition of vapor pressure and how IMFs affect vapor pressure.